Today's objectives are straightforward. You need to be able to write an empirical formula by the time we're done with this, so you will also obviously know what that is. And then also you will need to be able to reverse engineer the molecular formula if I give you the empirical formula. Okay? So, by now, you are familiar with both molecular formulas and formula units. But as a refresher, in case you've forgotten what those words mean, a molecular formula is for a molecule, so a covalently bonded compound, and it will show you the number and types of each atom in a molecule. And the formula unit will show you the smallest ratios of atoms possible in an ionic compound. Remember, it doesn't give you exact numbers because ionic compounds are lattices. So we don't get exact numbers, we get a ratio. Hopefully, these are old hat for you by now. You know what they are, because we're about to talk about one more type of formula. There's a third type of formula that we're going to call an empirical formula, because that's the name for it. Okay? An empirical formula is the symbols for the elements combined in a compound with subscripts that show the smallest whole number ratio of the different atoms in that compound. This should sound familiar because for ionic compounds, the formula unit and the empirical formula pretty much always the same thing because the formula unit already has the smallest possible ratio of atoms in that compound. Okay. However, for a covalent compound, for molecules, the empirical formula and the molecular formula are not always the same. Okay. For example, if we had C2H4, that would be our molecular compound. The empirical formula for that would be CH2. Smallest possible ratios. We have reduced it. Okay? So, there are some rules or steps that you can follow to find the empirical formula for a compound. Okay? Here's how we go. We begin by converting percentage composition to mass composition. So the percentage composition tells you what percent of this compound by mass is a certain element. We've been doing that, right? We've been calculating those. Okay? So you can do this by taking the formula, your molecular formula for the compound that they gave you, and then assuming that you have 100.0 grams of the compound, take those percentage mass ratios and turn them into weights in grams. Sorry, not weights, masses in grams. Okay? If you're not starting from percent composition, if you're starting from a mass composition that they gave you, you can skip this step. We're going to do an example problem that helps this make sense. We're just running through the steps first. Okay? Then, step 2 is to convert the mass composition of each element to a composition in moles by dividing by their molar masses. This will give you a ratio of moles, but it won't be reduced, and so you need to reduce it in order to use it to make your empirical formula. So, you're going to then divide each number of moles by the least number existing in the ratio, so the smaller number. And then because sometimes we round weird or we get weird data from experimental errors, it's very possible that when you do that division by the smaller number that you wind up with one number that's a whole number and one that's not quite a whole number that has some decimals on it. And that's okay because we can ignore those extra decimals and round to the nearest whole number, which is in fact your next step. Round to the nearest whole number and use the ratio of moles to write your empirical formula. So let's do an example problem. Quantitative analysis shows you that a compound contains 2.01% hydrogen, 32.60% sulfur, and 65.30% oxygen. Now we want to find the empirical formula. So they did not start us off with mass percentages. They started us off with just percentages, right? So we do need to do that step 1, where we pretend we had 100 grams of this substance, right? If we had 100 grams of this substance, how many grams of hydrogen would we have? 2.7. Yes, which is why we picked 100 grams, because it makes this step really easy, okay? So we would say if we have 100 grams of this substance, we would have 2.016 grams of hydrogen. We would have 32.60 grams of sulfur, and then we would have 65.30 grams of oxygen. The next step is to convert this to moles. So we need the molar masses of the substances that we're dealing with. Okay, so we are converting 2.016 grams of hydrogen. What's the molar mass of hydrogen? 1.01, yes, grams for 1 mole of hydrogen. And so then we would do the math, okay? Then we're going to do the same thing, 32.60 grams of sulfur. What's the molar mass of sulfur? Can somebody look and tell me? 32.07. Yep, 32.07 grams of sulfur is 1 mole of sulfur. And then 65.30 grams of oxygen. Molar mass of oxygen is 16.00 grams for 1 mole of oxygen. So now we can do this math. When we do the math, what we should roughly come up with is 2.001 moles of hydrogen. I'm sorry, it's so hard to write on this. Hopefully you can read my writing at least a little bit. Then 1.016 moles of sulfur, and lastly 4.081 moles of oxygen. So, next step, after we convert them all to moles, is to take those moles and divide them by the smallest number in the ratio. So what that's going to look like, I'm just going to go ahead and give myself a blank whiteboard and erase these that we just did. Okay, you're going to wind up with your ratio is 2.001 moles of hydrogen to 1.016 moles of sulfur. Wow, I don't know why I'm having such trouble writing today. To our 4.081 moles of oxygen. So now we're going to divide each of these by the smallest, which was our 1.016 on all of them. And what that comes out to is we come out to 1.969. Why did my pen stop working? Moles of hydrogen, followed by 1 mole of sulfur, followed by 4.019 moles of oxygen, and then the last step is to reduce this round them to their nearest whole numbers. So for the first one, nearest whole number is 2, right? So 2 moles of H to 1 mole of sulfur, and then the smallest whole number for oxygen is 4 moles of oxygen. So based on that whole number ratio, we know that the empirical formula then would be H2SO4. That's your empirical formula for this. Remember, this does not mean that it's the actual formula that has the actual number of each of them. This is the smallest whole number ratios. Okay? All right, let's exit out of this mode. You can use an empirical formula that somebody gives you to solve for a molecular formula if you have a measured molecular formula mass. Okay. And what that looks like is we can write out this equation and say that X times the empirical formula will give you the molecular formula. And in this equation, X stands for the number that the whole number that you must multiply the subscripts in the empirical formula by in order to get your molecular formula. That's a typo. It shouldn't say empirical formula twice. The second empirical formula should be molecular formula. Using the same formula, but substituting in masses instead of formulas, you can solve for X. So we can take the formula X times the empirical formula mass is equal to the molecular formula mass. So if you have then the empirical formula mass and the molecular formula mass, you can divide the molecular formula mass by the empirical formula mass to get your whole number multiple to then give you the molecular formula instead of just the empirical formula. Let's try an example problem of this. Okay, they have the empirical formula for a compound, and the empirical formula is P2O5. Through experimentation, they found that the molar mass of the compound is 283.89 grams per mole. They want to know what is the compound's molecular formula. So we're going to be using that equation that we had, the X times empirical formula mass is equal to molecular formula mass. Now, they didn't give us a molecular formula mass, did they? What'd they give us instead? Molar mass. Okay, but we know from our bell ringer this morning that molecular formula mass and molar mass are the same numerically. They just have different units on them. Okay, so in order to do this problem, we're going to be dividing the molecular formula mass by the empirical formula mass. Now, they did not give us an empirical formula mass, did they? We would have to solve for it by looking at the formula that they gave us up here, P2O5. So we have to go in and calculate the empirical formula mass, and then we have the molecular formula mass, and then we can divide them by each other to get that whole number. So let's put this in 283.89, and then we'll say U. And we're going to divide it by this that we're going to calculate. So what is the average atomic mass of phosphorus? 30.97, and then we're going to need to take that times 2. And then of oxygen, we know because we've been using it all day, 16.00, and this one's times 5. So what do we come up with if we take 30.97 times 2? 61.94, and 16 times 5 is 80. And so if we sum those up, we get 141.94. Is that what you said? So then if we do this division problem, 283.89 divided by 141.94 0.94, we come out with approximately 2.00, just 2.0, however many zeros you want to put after it. The number we are looking for here is 2. So that means if we then erase this and we take P2O5 times 2, we will get P4O10, and that right there is our molecular formula. Okay, this is the end of the notes. Okay.
Could you go back?
I can. Do you want me to put the
Writing of the first section.
Let me see if I can. What are we going back to?
Just one for the calculation.
I'm not sure if those are still there, but we'll try. That? Just draw a little arrow that this is the number we got. All right, that is going to be where we stop that.